My work is about large-scale phenotyping using tensor factorization on Apache Spark. The goals are twofold. One is to parallel tensor decomposition on Spark platform, and then to discover useful phenotypes for large-scale tensor. So the background is one is what is tensor. Tensor can be interpreted as a multi-way array. This is a third-order tensor here with all non-zeros marked as dots. And there are several tensor operations. We focus on time matricized tensor times quadrilateral product, MTTKRP for short, because it is the bottleneck of CP decomposition. For CP decomposition decomposes a tensor as a sum of component rank 1 tensors. It is an important algorithm for phenotyping. We represent the rank using R here. This work, we focus on CPLS algorithm. CPLS takes a sparse tensor and a given rank R as input and output the sequence of factor matrices. There are two loops here. The most important operations are the two steps. The first is the Hadamard product sequence, with each matrix doing the matrix multiplication, and thus to generate the updates the way. And the second is the MTTKRP. Let's introduce our parallel CP-ALS. First, we designed three main data structures. This is a third-order sparse tensor in coordinate format. Each row represents a non-zero entry, and with its value. First row is with its value 1, and these are three indices, I, J, K. And the SP10 tuple is the class represent each non-zero entry here. And the SP10 and SP10 RDD represent a sparse tensor locally or distributed. With three other members, the number of dimensions, the number of non-zero entries, and also the tensor size. And the difference is the local SP10 we use the array to represent all the tuples, and for the distributed tensor we use RDD to distribute the sparse tensor. Now our parallel MTTKRP algorithm is like this. We have two parallel sections. The first section is to compute each non-zero entry of a tensor with a row vector from matrix C to generate another row stored in Y. After the first parallel section, we get an intermediate tensor Y, and then in the second parallel section, we do the element Y's with each vector from Y and the matrix row vector from matrix B to update the matrix MA. And for our parallel CPLS, we have the parallel MTTKRP algorithm, and the other optimization is to use the incremental update to update the matrix way here. So we don't need to compute all the matrix multiplication from scratch, but we only compute the AN and AN inverse and AN here. And then we do the Hadamard reduce to update V. Now let's see our experiments. So because we use parallel data structure and distributed data structure and parallelize it on Spark, we should have better performance. We compared 4 implementations. The first two P vector, PVEC means the parallel, our parallel algorithm, in parallel, and SVEC is our algorithm in sequential. Pint and Sint are the most straightforward algorithm in parallel or sequential. So we test on two data sets. The first is a small tensor generated synthetically from tensor toolbox, and the other is a mimic dataset generated from mimic3. So for the small tensor, our algorithm gains better performance, either in parallel or sequential one, but but our parallelism don't have much benefit. On the mimic data, our parallel algorithm actually worse than the sequential code. So we analyze the reasons. One reason is we use expensive matrix to transpose because Breeze stores the matrix in column major format, but we need to compute each row, so we need a lot of matrix to transpose. And another reason is maybe we need to use more larger data than Mimic-3 dataset. We also test our algorithm using different ranks. It shows that our algorithm is stable and it is possible to compute more phenotypes each time. And this is our most generic phenotype discovered. Overall, we designed the new algorithm formatted and new tensor operations on Spark. And we propose the two parallel algorithm and evaluate on Mimic-3 dataset. Although we don't get speedup, but for large tensor which cannot resident in memory, our algorithm can easily handle that. That's all. Thank you.